I submitted 50 resumes targeting hardware engineers, but none of them were responded to. Stop telling yourself it's just because the overall job market is tough. But today I want to reveal a counterintuitive truth. You can still land a hardware engineering position without an internship, provided you develop these 4 key skills. The last one is something 90% of fresh graduates haven't even heard of. The first skill is power supply fundamentals. Don't assume designing a power supply is as simple as drawing an LDO circuit or adding a capacitor. Let me ask you 3 questions. If you can't answer them, you'll receive 0 points on this aspect. First, how do you measure DC-DC ripple? How should you connect the probe? Should you touch directly to the pins or use a grounding spring? Can the measurement error vary by up to 10-fold? Second, why do some secondary diodes and flyback power supplies use Schottky diodes while others use fast recovery diode? If you answer, because of the lower voltage drop, the interviewer will simply shake their head. Third, how should the power on timing be controlled? Should we use an RC delay circuit or the PG pin on the power supply chip? Which approach is more reliable and which one is more cost-effective? Listen carefully. In hardware position interviews, power supply is a mandatory topic. Even if you've never interned, simply explaining these 3 concepts thoroughly and demonstrating your self-built buck converter circuit will immediately catch the interviewer's attention. After all, most fresh graduates can't even hold a soldering iron properly. The second category involves MCU peripheral circuits. Don't claim you can write Arduino code or control LEDs that defines a programmer, not a hardware engineer. What does a true hardware role really require? It depends on your ability to design the minimum system for an MCU. How do you match capacitors in the oscillator circuit? Why is a 104 capacitor element needed in the reset circuit? How should boot pins be handled? And which interface, SWD or JTAG, should be used for the download circuit? There's an even more critical aspect, signal integrity. Why is the pull-up resistor for I2C set to 4.7 kiloohms? How should you handle excessively long SPI traces? What are the differences between MAX 232 and CH340 in terms of UART level conversion? Let me share a real-life example. Last year, there was a student who didn't have an internship but built his own STM32 development board from schematic design to PCB fabrication, soldering, and debugging all on his own. For this single project alone, he received 5 job offers with the highest monthly salary reaching $3,000. Take a close look at that. The third category is PCB fundamentals, the essential skill set for any hardware role. Your proficiency with Altium Designer directly determines whether you'll pass the technical interview. But let me remind you, knowing how to pull wires doesn't mean you can design a PCB. Let me ask you, how should the power plane and ground plane be separated? Why is impedance control necessary for high-speed signals? How should differential pairs be routed? What about equal-length routing? Is it feasible to place vias directly on solder pads? Then there's the most easily overlooked aspect, EMC and EMI. Why can't traces run beneath the crystal oscillator? Why are ESD devices required at interfaces? And is a shielding cover really necessary? If you can clearly explain these points and then present your designs for 4-layer and 6-layer boards, I guarantee the interviewer will immediately offer you a position. Most fresh graduates only know how to design 2-layer boards, and even those use through-hole component. Wait, do you really think covering these 3 types is enough? You're completely wrong. I've met too many people who claim to understand power supplies, MCUs, and PCBs speaking eloquently during interviews, but when it comes to hands-on practice, their true capabilities immediately reveal themselves. Why? Because he lacks the most crucial 4th type of capability, debugging tools. You might find this hard to believe, but 80% of a developer's working time isn't spent drawing diagrams, it's spent debugging and troubleshooting. If you can't use your tools effectively, is your employer hiring you just for show? The 4th category, debugging tools. This is the key distinction between theoretical knowledge and practical expertise. Here's a list for you to check off one by one. First, the multimeter. Don't laugh, 90% of people use it incorrectly. What's the difference between the open, closed, and resistance ranges? Why can the diode range measure voltage drop? Should current be measured in series or parallel? And when a fuse blows, you might not even know why. Second, the oscilloscope. It serves as a second pair of eyes for hardware engineers. How do you calibrate the probe? What trigger mode should you choose? How do you measure rise time? What is the relationship between bandwidth and sampling rate? If you don't even know how to set the 20 MHz bandwidth limit, you'll never be able to accurately measure ripple levels. Third, power supply. How should an adjustable power supply be used? How should current limiting protection be configured? Is overcurrent protection set to constant current or surge protection? If the board shorts, should you power it directly or first measure its ground resistance? Fourth, the logic analyzer. How do you analyze I2C, SPI, and UART protocols for packet capture? How do you identify issues caused by incorrect timing sequences? Listen, you don't need to purchase each of these tools individually. However, you should at least understand the purpose of each instrument, its appropriate application scenarios, and the basic operating procedures. During an interview, when the interviewer asks, How did you identify this bug? It's sufficient if you can clearly explain your troubleshooting approach from using a multimeter to operating an oscilloscope. This is especially important since most fresh graduates don't even know how to connect an oscilloscope probe. Finally, there's another hidden bonus: your ability to conduct project reviews. What does this mean? It means that after completing a project, you should be able to clearly explain what problems did you encounter, how did you diagnose them, how did you resolve them, and what lessons did you learn. For example, you developed a power module with significant output ripple. How did you diagnose it? Did you start by replacing capacitors or measuring the circuit? Was the issue related to layout design or compensation settings? What adjustments were made in the end, and how much did the ripple decrease? If you can explain this entire process in detail, it will be far more effective than simply stating, "I've completed 10 projects." This is because interviewers are not interested in the quantity of projects you've done, but rather in your ability to think critically and solve problems. Now we've covered 4 key areas: power supply fundamentals, MCU peripherals, PCB basics, debugging tools, plus a project review session. Which category are you missing? Let me know in the comments and I'll help you identify what you need to improve. Follow IC Want Open for more hardware interview tips and real-world electronics engineering breakdowns.